one thing notable about these formalization projects is that they allow massive collaborations. So in other sciences, people collaborate with 20 people, 500 people, 5,000 people. But in mathematics, still, we don't really collaborate in really large groups. 5 is kind of the maximum usually. And part of it is that, if you want to collaborate with 20 people, if you don't already know these 20 people and you don't completely trust that they're doing correct mathematics, it's very difficult because everyone has to check everyone else's contribution. But with a proof assistant, the proof assistant provides a formal guarantee. And so you can really collaborate with 20, hundreds of people that you've never met before. And you don't need to trust them because they upload code and the lean compiler verifies, yes, this actually solves the problem they claimed, and then you can accept it or it doesn't. So I experienced this myself because I got interested in formalization a few months ago. So I'd recently proven a combinatorial theorem with Tim Gowers, Ben Green, and Freddie Manners. It solved something called the polynomial Feynman-Ruzha conjecture. The precise conjecture is not important for this talk. It's a conjecture in combinatorics. You have a subset of a finite field vector space of small doubling, and you want to show that it is very close to actually being a coset of a subgroup. This was a statement that was in additive combinatorics that was highly sought after. So we had a 33-page paper recently proving this, mostly self-contained, fortunately. So I thought it was a good candidate for formalization. So I asked on an internet forum specializing in lean for help to formalize it, and then again, like 20, 30 people joined in, and it actually only took 3 weeks to formalize. So the time taken to formalize these projects is going down quite a bit. So in particular, the time taken to formalize this project was roughly about the same time it took for us to write the paper in the first place. And by the time we submitted the paper, we were actually able to put as a note that the proof has actually been formalized. So as I said, it uses this thing called a blueprint, which splits up the proof into lots and lots of little pieces. And so it creates this nice little float, this little dependency graph. So this is a picture of the graph at an early stage of the project. So there's this node down the bottom called PFR. Maybe only the people in the front can see it. That's the final theorem that we're trying to prove. At the time of the screenshot, this was white, which means that it had not been proved, but not even been stated properly. So in fact, even before you prove the theorem, you have to first state it, and then you have to make definitions and so forth. Blue are things that have been defined but not yet proven, and green have been things that have been proven. And so at any state of at any point in time, some bubbles are white, some bubbles are blue, and some results depend on some others. And so the way the formalization proceeded was that different people just grabbed a node that was ready to be formalized because maybe all the previous results, all the results that it depended on were formalized, and they just formalized that one step independent of everybody else. And you didn't really need to coordinate too much. I mean, we did coordinate on an internet forum, but each little node is completely specified. There's a very precise definition and a very precise thing to prove, and we just need the proof. And we really don't care exactly what the proof is. I mean, it has to be not massively long. But so people just picked up individual claims. Like here's one very simple claim. There's a certain functional called Ruzha distance D, and there's a very simple claim that it was non-negative. And this turns out to have a 3-line proof, assuming some previous facts that were also on the blueprint. And so people just sort of picked up these things separately, and over time it just filled up. This is what a typical step in the proof looks like. This is the proof that this Ruzha distance is non-negative. This is the code in lean. It looks kind of a little bit like mathematics, but it is actually, if you've once you're familiar with the syntax, it actually reads, it's like reading LaTeX. First time you read LaTeX, it looks like a whole bunch of a mess of symbols. But every line corresponds to a sentence in mathematical English. For example, the first line, if you want to prove that this distance is positive, it suffices to prove that twice the distance is positive. So you work with twice the distance because it turns out there's another lemma that bounds twice the distance. So yeah, every step actually, it corresponds reasonably well to the way we think about we write mathematical proofs. Yeah, so fortunately the proof didn't reveal any major issues. There were some typos, but very, very minor picked up. And we also, there were some things we needed to add to the math library. There was the math library, we used Shannon entropy, and Shannon entropy was not in the math library, now it is. One thing about formalization is that it still takes longer to formalize proofs than to write them. And maybe about 10 times longer, I would say. Which is unfortunate. If it was faster to formalize, to write the proofs formally than to write them by hand, I think then that would be a tipping point. And then I think a lot of us would switch over, just because to get the guarantee of correctness. So we're not there yet. It is definitely getting a lot faster than it was before. But one thing we noticed is that actually, while it still takes a long time to write a proof, if you want to modify a proof to change some parameters and make it a little bit better, that can be done much quicker in the formal setting than with a paper proof, because with paper proof, if you change all your little parameters and so forth, you're likely to make also mistakes, and you go back and it's a very annoying process. But it's actually much easier to modify an existing formal proof than to create one from scratch. For example, there's a constant 12 exponent that appeared in our proof. A few days afterwards, someone posted an improvement in the argument that improved 12 to 11, and in a few days we were able to adapt the formal proof to do that as well. Yeah, and because you can collaborate, I think the process is scalable. There's just recently, Kevin Buzzard, for example, launched a 5-year project. The aim is to formalize Fermat's last theorem, the proof. And that is quite a big goal, because there are lots and lots of sub-portions that have had no formal proof at all. So that, I think, will be quite an ambitious project, but I think it's now doable. It wasn't doable 5 years ago, but now I think it is. Okay, so that's formal proofs. All right, so machine learning using neural networks has become also more and more commonplace in different areas of mathematics. I think I'll skip over this one. So one place where it is being used is in PDE to construct candidate approximate solutions for various problems. So so there's a famous problem in fluid equations, do the Navier-Stokes equations blow up in finite time? Do the Euler equations blow up in finite time? Navier-Stokes is still challenging, but Euler, there's been a lot of progress recently that people have been starting to construct self-similar solutions to the Euler equations with some asterisks, but the asterisks are slowly being removed. And one of the strategies of proof is to first construct an approximate solution, approximately self-similar solution that looks like it's going to blow up, and then use some rigorous perturbation theory to perturb that to an actually blowing up solution. And machine learning has turned out to be useful to actually generate these approximate solutions. But I'm going to skip that for lack of time. I'll tell you, my favorite application of machine learning to mathematics is in knot theory. So this is a recent work. So knots are a very old subject in mathematics, and there's lots of one of the fundamental things you study in knots is knot invariance. So there's various statistics you can study, you can assign to a knot, which depends on the topology of the knot or the geometry of the knot. So there's something called the signature, which is a combinatorial invariant. There are these famous polynomials, like the Jonas polynomial and Homfly polynomial. Then these things called hyperbolic invariants. The complement of a knot is often a hyperbolic space, and then you can talk about the volume of that space and some other geometric invariants. And so there are these massive databases of knots. You can generate millions of knots, and you can compute all these invariants. But they come from very different areas of mathematics. So some knot invariants come from combinatorics, some come from operator algebras, some come from hyperbolic geometry, and it's not obvious how they're related. But what these mathematicians did was that they trained a neural network on this big database of knots, and they studied the hyperbolic invariants and the signature, which is the combinatorial invariant. And they found that you could train the network to predict the signature from the hyperbolic invariant with like 99% accuracy. So they used like half the data to train the set and then half the data to test the set, to test the neural network. And so what this told them is that there must be some connection. The signature of a knot must somehow be a function or at least very closely related to a function of a hyperbolic invariance. But the problem with neural nets is that they give you a functional relationship, or at least a conjectural functional relationship, but it's this massively complicated function. You compose hundreds and hundreds of nonlinear functions together, and it doesn't give you any insight as to what the relationship is. It just tells you that there is a connection. But it's possible to do some analysis. So they actually tried a very basic thing which happened to work. It's what's called a saliency analysis. So this neural network gave them this function. Basically, they fed in 20 hyperbolic invariances as input, and the signature as output. So it's basically a function from R to the 20 to the integers, I think. And what they started doing is that once they had this function, they just tested how sensitive the function was to each of its inputs. So they just varied one of the 20 variables, and they saw what happened to the output. And what they found was that only 3 of the 20 variables were actually important. That only 3 of them had a significant influence on the function. The other 17 were basically not relevant at all. And so they focused on those 3 variables, and they started plotting this function just restricted to those 3 variables. And that's just low enough dimension that you can eyeball the relationships. So they started plotting the signatures as a function of 2 or 3 of these variables, and using color and so forth. And they started seeing patterns, and they could use these patterns to conjecture various inequalities and various relationships. It turns out that the first few inequalities they conjectured were false, and they could use the neural net and the data set to confirm this. But with a bit of back and forth, they were able to eventually settle upon a correct conjecture relating these invariants to the signature. And it wasn't the invariance that they expected. So yeah, it was these. They were expecting the hyperbolic volume, for example, to be really important. It turned out not to be relevant at all. But once they found the right variables and the right conjecture inequality, it suggested the proof. And then they were able to actually find a rigorous proof of the inequality that they conjectured. So it was a very nice back and forth between using the machine learning tool to suggest the way forward, but then going back to sort of traditional mathematics to prove things. Okay.